Let's increase the complexity of our model and talk about linear regression. This is the mathematical equation for the type of model that we're going to try to fit to our data. The predicted y values are equal to some number, beta 0, plus some other number, beta 1, multiplied by the value of our feature. In this case, we only have one feature. We were using age as that feature. This is the model, and it graphically represents some sort of line. We want to find the best possible line. Again, the one that reduces the mean square error. So we need to find our intercept, our beta 0, and our slope, beta 1, that reduce our mean squared error. There's going to be quite a bit of math here. However, hopefully it is a rewarding process. Again, we start with our mean square error. Now we can replace our predicted y value with our model, which is beta 0 plus beta 1 multiplied by our feature x. Now we can distribute in this negative. Of course, we're going to try to reduce our mean square error. So again, we have to take the partial derivative of our mean square error in relation to beta 0. First, we'll try to find what beta 0 value we need to reduce our mean square error. And this is a derivative. Now we can set the derivative to 0 to find our minimum value. We can get rid of our negative 2 over n. And because addition is commutative, we can break up the addition into these three sections. Now, the sum of our beta 0s is the sum of a constant. And how many beta 0s are we going to have? Well, it depends how many predictions we're making, how large our training set is. And we'll say our training set is length n. So we have n beta 0s. Now we can move our n beta 0s over to the other side and then divide by n, or multiply by 1 over n. If you notice, what this gives us right here is the average of the y values, or the mean of the y values. And what this gives us here is the average of the x values, or the mean of the x values. So we can use our bar notation for that. So to reduce our mean square error, our intercept, or our b0 value, our beta 0 value that is, has to be equal to the mean of our y values, subtract whatever beta 1 is, multiplied by the mean of our x values. Of course, the problem is we don't know what beta 1 is yet, which means we have to do the same process on beta 1. Again, we start with mean square error. We're going to substitute our model in for our predicted y value. And we can do the same distribution, distribute in the negative, and we're going to take the derivative, the partial derivative of our mean square error with respect to beta 1 this time. And this is what that derivative will look like. Once again, we have to set it to 0. We can get rid of our negative 2 over n. And we also have to distribute in this x. So we get xi multiplied by yi minus xi multiplied by beta 0 minus beta 1 multiplied by xi squared. Again, since addition is commutative, we could break this into three parts. These constants can be factored out. We're going to replace beta 0 with this. If you recall, this is what we found for beta 0 last time. It was the mean of the y values minus beta 1 times the mean of the x values. So we're going to sub this in. Now we're going to distribute our sum of our x values and also our negative into the brackets. Which brings us to this. I know it's quite a long line. If you need to pause and look at the math yourself, definitely do that. Okay. So what we've done here is we had the sum of xi multiplied the sum of xi, which gives us the sum of xi squared on the next line. Now we can move this section over to our left-hand side. We can factor out these beta 1s. On the left-hand side, I simply just flip the terms to make it look a little bit nicer. Then to get beta 1 on its own, we can divide by everything else that's on the right-hand side besides beta 1. And again, to do some cleaning up, we can multiply the top and bottom by n. And finally, this gives us the beta 1 value that reduces or minimizes our mean square error. So in summary, to find the line that best fits our data according to the least squares method, or reducing our mean square error, these are the values that we need. Beta 1 should be equal to this calculation, and beta 0 should be equal to this calculation. And as you can see, in order to find these values, you'd start by calculating beta 1, which just depends on n, our x values, and our y values. And then you can calculate beta 0, which involves already knowing beta 1.